This is 3 basic electric fields problems. Some of them have multiple parts, but we'll cover most of the basics for solving for electric fields. Question 1. A negative test charge experiences a rightward force of 5.96 times 10 to the minus 8 newtons at a point where the electric field intensity is 0.000169 newtons per coulomb. Find the charge of the test charge, find the direction of the electric field, and if a proton were placed in the electric field, what would the force be on the proton, magnitude, and direction? So let's solve for part A first. Part A asks us to find the charge of the test charge. Well, we know the force on the charge, and we know the electric field intensity, that's capital E. These are both vectors. And so we use our equation, E equals F, capital F over Q. To solve for Q, we multiply both sides by Q. We get Q equals, or Q times E equals F. QE equals F. Divide both sides by E, we get Q equals force over E field. Plug in our numbers. 5.96 times 10 to the minus 8 newtons divided by our electric field, 0.000169 newtons per coulomb. Newtons cancels. Divided by 1 over coulombs gives us coulombs, so our answer is going to be, well, we'll plug it into a calculator. 5.96 times 10 to the minus 8 divided by 0.000169. We get 352 times 10 to the minus 6 newtons. Whoops, not newtons. Units are coulombs. Another way of writing that is 352 microcoulombs. Okay, part B. Find the direction of the electric field. Well, let's sketch out a diagram for this. We have a negative test charge, so I'm going to call this our test charge little q, and it experiences a rightward force to the right. So we know that positive charges feel a force in the direction of the field, which means negative charges feel a force opposite the direction of the field. So our field is going to be pointing to the left. I'm sketching out a uniform electric field around that test charge, but we don't actually know if it's uniform. But that just shows us the direction. So E field is left. Part C. C is find if a proton were placed in the field, what would be the force on the proton, magnitude, and direction? So we know that E equals F over Q. So that means that force is just equal to charge times electric field. Okay, so we plug in our numbers. The charge on a proton is little e, 1.60 times 10 to the minus 19 coulombs. And the electric field is given as 0.000169 newtons per coulomb. Coulombs and coulombs to the minus 1 cancel. We end up with our final answer, 1.6, 10 to the minus 19 times 0.000169 gives us a pretty small force of 27.0 times 10 to the minus 24 newtons. And that's the magnitude of our force. Since we know that our electric field is pointing to the left and a proton is positive, a positive charge is going to feel a force in the direction of the E field, so the direction is left. That's part C. Let's move on to our next problem. An alpha particle is a nucleus made of 2 protons and 2 neutrons. Alpha particles are the products of a particular type of radioactive decay, called alpha decay. Sketch the electric field around the alpha particle. I'm going to zoom out just a little bit. Find the electric field produced 3.0 millimeters away from the alpha particle, and find the electric field produced 1.5 millimeters from the alpha particle. Okay, so A, an alpha particle is 2 protons and 2 neutrons, which means it is neutrons have a charge of 0, so the protons are the only thing that's going to produce a charge. So our alpha particle is something like a positive charge, and it has a charge of plus 2e. So our electric field lines point radially away from a point charge, and they should be pretty evenly spaced around my point charge. So that's the electric field around a positive charge, my alpha particle. Okay, B. Find the electric field produced 3 millimeters away from the alpha particle. Okay, well, this is a point charge, and we know that the electric field around a point charge is E equals K Q over R squared, where Q is the magnitude of the charge and R is the distance from the center of charge of that charge. So let's just plug in our numbers. K is 8.99 times 10 to the 9 Newton meters squared per coulomb squared. Q is the magnitude of the charge. It's 2e, so it's 2 times 1.60 times 10 to the minus 19 coulombs, divided by our distance squared. Our distance is 3 millimeters, so we need to convert that to meters. 3.00. Milli means 10 to the minus 3, so times 10 to the minus 3 meters, and that whole thing squared. Let's cancel out our units to see if we get sensible units. Coulomb cancels out with coulomb once. Meters squared cancels with meters squared. And we'll end up with newtons times coulombs over coulomb squared, or newtons per coulomb. That's good. That's the unit for electric field. Let's plug in our numbers and see what we get. Getting 319, 320 really, 320 with a decimal point, 320 times 10 to the minus 6 newtons per coulomb. 320 times 10 to the minus 6 newtons per coulomb. We could also write that as 320 micronewtons per coulomb. There's our answer. Part C. Find the electric field produced 1.5 millimeters from the alpha particle. Now, we could just plug in the numbers again, calculate that again, but I'm just going to use proportional reasoning. I know that electric field, since it's kq over r squared, it's proportional to 1 over r squared. So that means if I take the distance and multiply it by 0.5, and that implies the electric field is multiplied by 1 over 0.5 squared. So I'm just going to take my answer, my previous answer, and multiply it by 1 over 0.5 squared. So my electric field is equal to 320 micronewtons per coulomb times 1 over 0.5 squared, 1 over 0.5 squared, and that's equal to that is equal to 1.28 times 10 to the minus 3 newtons per coulomb, which is equal to 1.28 millinewtons per coulomb. Now I plugged in 10 to the minus 6 for micro right here, and that's probably a good idea for you to do too. 10 to the minus 6 newtons per coulomb. And then it just gives it to me in newtons per coulomb, and then I convert it at the end. It's much stronger because it is a lot closer. It should be actually 4 times stronger. Because we cut the distance in half, electric field is multiplied by 2 squared, inverse square law. Okay, last question. A thundercloud above the Earth can be modeled as a negatively charged thundercloud separated from the positively charged ground. Suppose a thundercloud has a net charge of negative 34.0 coulombs, and the ground immediately below it, 1950 meters, has a charge of positive 340 coulombs. What is the electric field, magnitude, and direction exactly halfway between the cloud and the ground? What direction will electrons flow if lightning strikes? So I'm going to sketch out a diagram for this one. We have the ground, we have a cloud, and we know their distance of separation is 1950 meters. 1950 meters. We know the charge on our cloud, I'm going to call Q1, equals negative 34.0 coulombs. And we know that the charge down here on the ground is positive, Q2 equals positive 34.0 coulombs. What is the electric field, magnitude and direction, exactly halfway between the cloud and the ground? So we're not actually looking at the force between these two opposite charges. We're looking at the electric field right here in the center. So let's just think about, before we do anything else, how we're going to do this. Well, each of these charges produces an electric field independently of the other. Negative charges produce an electric field that goes towards the negative charge. So I'm going to call this vector represents the electric field from the thundercloud, E1. Positive charges produce electric fields that go away from the positive charge. So this ground is going to produce an upwards electric field, E2. Notice that both of these electric fields are in the same direction. We can also think about how we're going to calculate that electric field. We're going to use the electric field caused by a point charge equation. E equals K Q over R squared, where big Q is what's producing the electric field. So let's calculate the electric field, let's say for the negative charge. So I'm going to plug in E1 is KQ1 over R squared. So that's 8.99 times 10 to the 9 times negative 34 coulombs. Put those parentheses on the outside. Divided by, well, the distance from the thundercloud to that center point is 1950 over 2. And that's just going to be 975 meters, 975 meters. So divided by 975 meters squared. Really probably shouldn't put units in here because I didn't put units in K. 4.0. And we plug in to get our electric field. It's a pretty strong electric field. It gives me a negative number, but I already know the direction of the electric field, so I'm not going to worry about that negative. The magnitude of the electric field is 321, actually 322, times 10 to the 3 newtons per coulomb. Or we could also write it as 322 kilonewtons per coulomb. So 1 coulomb feels 322,000 newtons of force at that point. So that's our first E, E1. Now we can solve for the second E using the same process. Actually, let's add the direction. E2, same formula, K Q2 over R2 squared. But here's what we know. The magnitude of charge 2 is the same as the magnitude of charge 1. And the distance from charge 2 to this point is the same as the distance of charge 1 to this point. So all of the numbers are going to be the same, except maybe the sign of our electric field. So from the symmetry of this situation, we know that E2 has to be equal to E1, equal in magnitude. So instead of solving it, we're just going to use symmetry. We know that E2 equals E1, which is also equal to 322 kilonewtons, 322 kilonewtons per coulomb. And the direction's the same too, up. So our net electric field is just the vector sum of all of our other electric fields. Since they both point up, we're just going to add them. So we have 322 up plus 322 up. That's 2 times 322 kilonewtons per coulomb, which gives us 644 kilonewtons per coulomb, and the direction is up. Just find the electric fields from each and add the vectors, but symmetry makes this problem a lot easier. That's all. Hope that's helpful. Bye.